Okay, so we are stepping into data structure. We are not covering the whole data structure in this class, but we want to kind of step into it. Some of these things coming in from your CS2, so you gotta know some basic parts of it. And we just want to see how is it done in Java. And then we're going to be looking at some of the collections or tools that's available in Java that you can use. And we're going to go through that. So some of the software engineering tools, data structure tools that's available, we're going to be talking about it, and I tell you what you have to be concerned about for your test, and then we go from there. So you should know about the sorting and searching. The idea is what? If I am just searching for something, then in average, I'm going to go through the whole worst scenario. I'm going to go through the whole list to find it. Best scenario is going to be the first one I'm looking for. So that's the search we do. And to improve that, then we might be doing some sorting that I can, let's say, by element 2, I might know that my search is not going to find it in the list, so don't look for the whole thing. And of course, there are some other algorithms for searching that can use the sort as a tool. But of course, every time we do an algorithm, it's going to cost something. So we're going to go through our cost, which is our time efficiency of our code. And we're going to talk more about those. I am not too concerned about the calculations. You guys are going to see these coming up in your data structure, in your algorithm class. You're going to spend some time to calculate these things. I just want to show it to you, but I'm not worried about calculating those things. So if we're talking about the selection sort that you had it in your CS2, the idea of the selection sort was you would start from the beginning. And so if I have this list, then I start with the beginning. I look for the smallest element in the rest of the array, and then I swap. So in this case, I have 11 over here, and then I go look through my list. I find the smallest one, then I swap. So 5 comes here, 11 goes there. Then I go to the next element. I have 9 here. I look for the rest of the list. I don't have anything less than 9, so I'm not going to do anything with 9. Then I go to the next element, which is 17. I look with the rest of the list. I find something smaller. I swap it. Same thing goes on, and then I'm going to be sorted. So not the best sorting algorithm, but this is the selection sort that happens. So I have to look at the rest of my list to find the smallest one, and then I have to do the swap. And then we're going to talk about the cost of these things. Stop me if you have any questions. So the steps is you're going to start some kind of a loop. You're going to find the smallest one in the list. You're going to do the swap, and then you're going to repeat till you finish up the whole list. When unsorted portion is of length 1, we are done. So we have 2 sections, the sorted section, unsorted section. So we have to go through the lengths, but because we are looking at the next element, we want to be sure that we don't go all the way through the array. So because we are always, wherever we are, we're going to be looking at the rest of the array. So if I am on index 2, I'm going to be start looking at index 3 to the end of the array. So if I am in the last element and I try to look to the next one, then we're going to have a problem. For that reason, we are going to stop one before that. So we don't go to a length, we're going to go with -1, so we don't go all the way to that. Then we are writing methods to be sure we do everything in organized way. So we have a loop, we find the minimum of the array starting on that index, wherever we are, and we're finding the minimum, and then we swap it. So for swapping, I need my array, I need my minimum position, and I need my current index. So we are focusing on methods. We want to do one method that's going to do one thing for us, one task. And when I'm writing that method, I'm not worried about where is it coming from. So when I am looking for minimum position, okay, I guess I don't have it here. So when I am looking for a minimum position, I'm not thinking about where my array is coming from, where my index is coming from. All I know is I'm going to start with that index. I'm going to be looking into the rest of the array. I'm going to find the minimum. I'm going to return it. When I'm focusing on this function for the swap, I know I have an array. I have two positions that I'm swapping the values for these two positions. So when I'm focusing on one method, I am not thinking where is it coming from. I'm just saying I'm going to focus on that method. For this method, I need an array and an index. For this method, I need an array and two positions that I'm going to swap. That's all I'm going to be focusing on. So to do that, we can put some random number in there, and then we're going to be printing it. Remember, we're going to do the toString for it to be able to print it, and then we're going to call the sort that we created, and then we're going to print that one. So we're going to create a utility part class to do something for us. In this case, we're going to create random int, and we're going to put it into our array. So that's the utility we're going to be using. Remember, this is not my whole program. I'm just going to use this utility to test to see my algorithm is working. So my focus is to create a class and methods to do my sorting for me, the selection sort. For that, I need to put some random number just to test it. So I'm doing this just for testing my algorithm to be sure it's okay. So when we are calling it, it's going to do that. So there's going to be the length and the number. So we're going to be creating that many elements with the range of the n that's coming in. And then we're going to return our array list over here. I'm not going to go through this because we have some stuff to do. Okay, now, so one of the things that you're going to be working in your algorithm class and partially in your data structure is this algorithm efficient comparing to other ones? Well, depends on where you are, what you're doing. Some of the things we do in computer science is to learn the stuff to see how does it work, what's the efficiency and those kind of things. And you may never ever come back to it, but at least you want to know what's going on. So one way of figuring out that one algorithm or a section of the code is working is to put some kind of a timer in there. So we can have some kind of a timer to check to see how long it's going to take for something to get done in a second, millisecond, or whatever it is. So we have something called current time in millisecond that we can call, and then we can create or use these things to start it, stop it, and then we have the starting time, ending time, and then we can deduct it and find how long it did it take. Then we can compare that to another algorithm and figure out how that's going to work. That's just checking the time takes to do something. Of course, that time depends to your machine, the processors that you're using, and all kind of things. But generally, the idea is not the amount of time that's used. The idea is comparing that to another algorithm to see what takes what. So to do that, we're going to create this one for the stopwatch, that we're going to have a reset. We're going to have a stop that's going to calculate our elapsed time. And then we have the start that we're going to check it to be sure it's running. In the stop, we're going to check it to see if it's not running. So if it is running already and I call the start, I'm basically not going to do anything. I'm just going to keep going. If I am in a stop and it is already a stop, and I'm calling the stop again, I'm not going to do anything. I'm going to return. So if it's not running, then I'm going to turn it that it is running to true. I'm going to call the start time in milliseconds. If it is on the stops no part, if it's already stopped, I'm not going to do anything. If it's not a stop, I'm going to make the is running false. That means it's already stopped. And then I'm going to find my end time, and then I'm going to find my elapsed time. Any questions so far? So we're going to get the elapsed time, and then, of course, our reset. That's going to reset some stuff for us. So that would be our stopwatch that we can use to check our algorithm. So to test it, we're going to have different numbers. So we can start with 10,000, we go to 60,000, and we're checking our selection sort. And we can see the numbers are growing as the numbers are growing. So that's what we are tracking of, that's what we are looking at. So we're going to be looking into this. Again, this is something that you should see it in your data structure course. I'm just going to go over it. I'm not worried about this too much. I just want to give you an idea how is it calculated. The calculation itself is not my concern, but you have to know what each one is. So this whole calculation, it shows up in your algorithm. It may or may not show up in your data structure, but that's the way we are going through the steps. And then when you know the steps, then we can go to continue on how we're going to be doing these things. So one way of checking your software, I hope when you're taking your software engineering, you would have this element in there. So one way of checking the software for what the cost is. So when you're writing the code, we're going to be checking some stuff in the code to see what does it take to get this code done. So if we focus on the sorting algorithm, the selection one, and we break it down, we are looking for the visits on elements. So if I want to find the smallest one, remember the first one is going to have to go through the whole array minus 1. The second one has to go through the whole array minus 2. The third one has to go through the whole array minus 3. And so it's going to have n elements plus 2 visit every time we go to the smallest one. The plus 2 is for the swap. So that's going to be in there. The next, the smallest one, and minus 1 plus 2, and so on. So if we add up those numbers, we can come up with some formula calculation on that, and then we looking at the smallest one to the largest one, and we don't need to calculate a fraction, so we're just going to cancel that thing, and we're going to come up to the number of visits is n squared. So that's the calculation. You want to do it, you can more than welcome to do it. I'm not too concerned about how we get here, but what I am concerned is in our algorithm, we're going to have something called big O notation. So the big O notation is going to tell us how this thing is going to change based the number of elements that we are looking at. So what it says basically that if I add more elements to my array, the sort is going to take a square of that. That means if I increase the elements of my array by 2, the time is going to take 2 to the power of 2, which is 4, to get it done. So we can see that this is going to be getting very bad when we have a lot of elements in our array. If it's a small number of elements, maybe it's not that bad, but when it gets to large numbers, and we can look at what we had before. So you can see 10,000 would take 786, but when we get to 60,000 is almost 20,000. So it's just related to the number of elements we are using. So some of these things, again, in your algorithm class, maybe you're going to calculate these things to know where we're going with these things. Right now in this class, I'm not worried about the calculation part, but you have to have some kind of idea, what does that mean? Maybe not exactly, but at least you have an idea what this means. So if I say O1, big O, 1, that means it's constant. It doesn't matter if you add the number of elements or not, it's always constant. So if I want to do swap, it's going to take me 2 visits to swap those things. It doesn't matter if you have 10,000 elements or you have 10 elements, that swap is always going to take 2 elements. Log n, and then we have n, which is linear. So we're going to be looking at that also. That's going to take whatever number of elements we have is basically directly dependent to number of element. As the number goes up, the big O is going to keep going up. Of course, log n, it increases, but in very slow pace. Then next to that one would be n log n. Then we have n squared, n cubed, 2 to the power of n, and n factorial. And again, we are not going to go through the calculation of these things. I just want you to know the ones that we have over here. So we're looking at insertion sort. Remember, with the insertion sort, what we were doing is we would have 2 half of array. The first part is already sorted. The second part is not sorted. So what we're doing in insertion part is let's look at this one right here. So I have, for example, this part is already sorted, and I am getting to number 5. I'm going to start with the middle, and then we're going to be worried about the boundaries. So if I am in the middle of this, I have a sorted part on the first part and unsorted part on the second one. It looks sorted, but that's not the concern. The concern is I am right here on, I have this part that's sorted, I have this 5 over here. Now, when I hit the 5, I'm going to compare 5 to the one next to it. If this one is a smaller, I'm going to swap it. Then 5 is going to come here. I'm going to check the 5. If it's smaller than this, I'm swapping. And then I have 5 here. If it's smaller than this, I'm swapping. So that's the way the insertion sort works. I have to be careful that when I'm going to the left, I'm not going to fall off to the left side. And because I am doing the checking with the previous one, I don't have to worry about the right end of my array. I have to worry about my left side of the array. I want to be sure I don't get the index -1. So that's what it is. So we start with, we shouldn't be starting with the first element because I cannot compare it with the next one. We should start with the second element comparing to this. And if it's a smaller, we're going to swap it. And then we go to the next one. This is not a smaller. We are not going to do anything. Then we go to the next one. This is smaller. We're going to move it to the right location. Then we get to 7. We're going to move it down to the right location. That's going to be right here. So that's the way the insertion sort works. Any questions on this? You guys had this in your CS2. That's why I'm going a little faster than normal. So again, we're going to have a loop. And remember, because we are concerned about the left side, I want to be sure that I don't start with 0. I start with 1 because I'm comparing to the left. So I got to create this loop that goes through the whole list. And then I am going to be looking at the element that I have wherever I am. And then I'm going to be comparing it to the previous one. But I want to be sure that I don't fall off the left side of my array. So I'm going to check it to be sure it's greater than 0. And I'm going to be checking for the left one. And then if that's, so if that's the case, we're going to be moving it. So you can see, of course, if we want to do the calculation, that's fine. The insertion sort is going to be n squared. That means as the number of my elements is going to get higher, the way that it takes to do the insertion is just going to be in power of 2. Are we okay so far? Okay, so this one is called merge sort. We're going to be using the recursion that we learned in the last chapter to bring it in our advantage to do merge sort. So what it does, it cuts the list in half, and then it's going to look at both half. And then it's going to cut it in half, then it's going to cut it in half, then it's going to cut it in half, just like we did the palindrome. And then when it finds the last element, then it goes one step up and it's going to merge it with the other one. So if we look at the array of this, we're going to cut it in half, then we're going to cut it in half, then we're going to cut it in half till we get all the way on, let's say 17. Then we're going to merge them with the previous one. Then we're going to merge them with the previous one. And then at the end, we're going to merge them together. So we're going to keep cutting it to get to the last element. And then we're going to merge them. So the algorithm would be looking at, we're cutting the lengths to half. So this is an integer division. So if it was odd number, we would have a different number, which is okay. And then we're going to get the two sides. and then we're going to call it recursively, the first part and the second. Now you can see something like this. You cannot get away without the recursion. So we are using a recursion. It does use memory a lot, but still we're going to do that. So it's going to go to the first one and second one. Remember, the second one is not going to happen till the first one is finished. So the first one is going to go back up. It's going to do the same thing. It's going to go back up. So it's going to be using a lot of memory, but it's just going to keep it doing it. And after it's done it, then it's going to merge them together. So it's going to go all the way down to one side. It's going to merge those. It's going to come back up. It's going to do, and it's going to put them together as it goes up. Of course, whenever you have recursion, you have to know where to stop. So the stopping point is very important. The first thing I always want to do before I do my recursion is where do I stop? Otherwise, my recursion is going to go forever. So if the length is 1 or less than 1, it can be 0. If it's even, we can get to the 0. We're just going to return. So that's my stopping point. So we run this for this many element. We're going to be testing it to see what does it take to do that. So going through the calculation, how many visits do we get, and how the subarray works, and how things are happening in there. And we can go through the whole calculation, which eventually you're going to do it somewhere else. I'm not worried about the calculation, but the bottom line is when we get to the end of this, it's going to come to n log n. So the big O notation for this would be n log n. So n squared is going to be the longest one, and then merge sort n log n is a lot better than n squared. So this is what we have comparing the selection sort versus the merge sort. Another one is called the Quicksort. So in Quicksort, we're gonna find a pivot somewhere. We're gonna partition it, and then we're gonna do that partition. So we're gonna sort each partition, and then we're gonna do it. In this case, I don't need any temporary arrays. On the other one, the previous one, we needed to have a temporary array to put them in there. So it's going to find the partition, and then it's going to sort that partition. And then, so we take it, we create a partition instead of putting it in another array, and then we're going to sort it from that partition. And then we're going to keep doing that partition. So instead of moving elements of the array, instead of copying stuff, we're just going to move the index pointer, and then we can partition. And doing that, so we can figure out the partition. There is different algorithm to do that, but we can potentially break it down to smaller partition, get this one sorted, get that one sorted, and put them together. So that's the way it's done. We're going to get the pivot. We're going to do the one before it. We're going to do the one after this pivot. This one is not done. And then we're going to keep doing it till we get the whole thing done. So in average, it's going to be big O n log n algorithm. its worst case is going to be O(n) squared. That is, if you're getting the pivots not the correct way, or we put the worst scenario on it. And so if the pivot was the first element, it would be basically like the first sort that we would have. So that's the way we're doing the sorting. And the whole idea of doing the sorting is we're going to have a better search algorithm. So the worst scenario for searching was linear search. Linear search means the best scenario would be the first element. I found it right away. The worst scenario would be the last element. So in average, it's going to cost me n divided by 2. So that means if I have 10 elements, in average, I'm going to have 5 visits before I find what I'm looking for. And because we don't use the fraction, we're just going to put the n, which is the maximum. So the search, linear search, is going to cost me big O(n). So that's going to grow as my list grows. Now we're going to look at some other algorithms. Before I forget, the Java has a utility called sort that you have seen it. Some of you guys have used it already. That is using a Quicksort to do the sorting. Okay, so if we have our array sorted, then we can use something called binary search. Binary search is going to look at it has to be sorted, so we're going to have a cost of sorting. Remember, linear search is not having any sorting, so it doesn't have that element of sorting. But if I want to do the binary search, my array has to be sorted. So it's going to be the cost of sorting and the cost of insertion and deletion. Because whenever you insert something in a sorted array, then you have to move things around. Whenever you delete something from sorted array, you have to move things around. So the cost of binary search is having a sorted array. We're going to have issues with inserting and deletion. And then we can do much faster search. So how do we do it? We're going to be cutting it in half. We're going to look at the middle point. If that's what we are looking for, we're going to be done. If we don't find it right there, we can go to the left or right based on the value. So if it's greater than what I have, I'll go to the right. If it's less than what I have, I'll go to the left. So that's the way we're going to do our binary search. So we are we cut this in half. I'm looking at 9. If the 9 is what I'm looking for, we're going to stop. If it's not, we're going to be cutting the other one in half, and then we're going to cut it in half. And we are looking for, what are we looking for? 15. So when we get here, we find out that the 15 doesn't exist. But the number of search is a lot better. The number of visits to elements are a lot better than our linear search that we had earlier. So in this case, 1, 2, 3, on the 4th element, we find out if it's there or not. So going through the calculation again, we can come up with log 2, which we're going to say it's a log n. That means as you increase the number of your element, the time that you need or the number of visits that you're going to do, it's going to be growing, but it's going to be growing very, very slow. So that means it's going to be very good for larger arrays. So linear search is big O n, binary search is n log n. And then we can decide which one we're going to be using. So we can go through the estimation of the time that we need. We don't have to check the whole program. We can go to a specific area and the algorithm. So again, if I need the binary search, I have to count into sorting, deleting, inserting in there. It's not just the binary search that's going to be good. What else do I need to get there? So that's the way we're going to be checking to see which one is going to be better. So in here, we are looking for most frequent element in an array. So we can be looking at the stuff. So we can count how often each element is occur, find the maximum count, and then respond it. So going through that, it's going to need the big O(n) for each visit to look at it. And we're going to need the count. So the total would be n times n, which is n squared. So that's the way you're going to calculate this. Again, the calculation is not my concern for this class. You will do that in your algorithm class, just an idea of how these things are done. So compute all counts is O big O n squared. Compute the maximum is O n. And then finding the maximum in the count is O n. And then we are going to pick up the n squared. So we can add more thinking into this. That's going to show up in your software engineering to find the most efficient way of doing things. So these are going to be in, for example, they are doing stuff in JPL. They are sending a rover to Mars. They want to find, and they have a limited space and they can do limited things. So they need to find the most efficient way of doing something. That way they can save on the actual hardware. If we don't need extra hardware, we don't have to put it in there. And then it's going to be more efficient. So you have people who are going to sit down and calculate these things to find the best algorithm to use. But most of us, we are not going to cross over this that much. We're either going to be doing some applications that we are going to use the collections utility to do it, or we are just going to be writing programs that's going to be running on the machines that we don't have to worry about these things too much. But again, just to get an idea how these things are done. So it goes over of how can we modify this algorithm to do a better way of doing it. So that is thinking beyond just the basic that most of us do to write our program. So Java library has this in there, and most of us going to be using just this one. instead of just sitting down and figuring out which one is going to be working. So that is going to be part of the collections that we're going to be visiting on Tuesday to see what's available in Java and why Java is getting so popular out there because of the things that's available to people.
Professor, question.
Sure.
So in the industry, do project managers just pick and choose which algorithms get implemented, or do developers have some flexibility on choosing what they want to implement?
So generally, the project manager doesn't know a lot about the coding. That's the problem with the industry. They cannot find enough technical people who want to be project manager. So when I am a project manager, I'm not only doing technical stuff, I'm doing some other stuff. So most of the technical people don't want to do other stuff. And so generally they're bringing people from the business department who may or may not know about the stuff. So you would have some kind of a senior technical people. There are some companies that I work with, they had two lines. They have technical project managers and they had business project manager, which they were involved with timing and vacation time, free time, or whatever they need to do. And hey, people are fighting with each other. Somebody has to take care of those things. And then they have technical people. So the senior technical people are generally when they decide after you did your business requirement, you go to the next step. They call it technical requirement. That's generally where it's going to be decided that what's going to be done. So when you're doing, so you did your design, when you start doing bottom-up design and top-down design, that is the time that you're starting with your technical design. In your technical design, you're going to be concentrating on these things. Now, the first thing that generally comes in mind is, does the language provide any tools? So for example, here, Java provides the tool sort. So the question is, if we use the Java collection tool sort, is that going to hurt us or not? And that actually going to depend to the industry. So the concern is what? If our software engineers, especially the technical senior software engineer, spend a lot of time to figure these things out, what's going to happen? It's going to cost us a lot more money. So if we just go use collection.sort, or basically any kind of it, it's not going to cost us any thinking, any time. The most expensive part of a software is our people and our senior people who are a lot more expensive than the juniors people. So that's the time that they have to decide that, are we going to spend time for figuring out the best algorithm, or we just use the language that's available? So having technical people who are very familiar with the language and have done these things before, then we have to decide on. So when we were working on airline security, that we were supposed to check everybody who's boarding, when we got to the point that, so we were asking at that time that all the information of the passengers would be sent to us 3 days in advance. So we have 2-3 days to process every person, to put a flag for red flag for the ones that we think, based not what we think, the requirements that they gave us. So we would flag the person or not. But then when you get to the point that the customer is at the counter, then we don't have that 2-3 days. So we had to do things differently to make it much faster. So that's the time that we have to sit down and say, okay, if we have 2-3 days, we're going to do it this way. If we have right now, then we have to do something to make it faster. So those are the decisions that generally your technical senior software engineer is going to do. Decisions that's coming from them, that they're going to decide, okay, we're going to do this way or that way. And that's the technical team. Did I answer your question?
Yes, you did. Thank you.
Oh, okay. So They are using the Quicksort for this algorithm. Maybe that's not going to be the best out there all the time, but in average, it's going to do whatever we need to do. We don't have to worry about calculating all this number. We don't have to worry about checking it with different algorithm, the size and all those kind of things. So you know what? We're going to use this. Yes, sometimes it's going to take a little longer, but hey, that's available. I don't have to write the code for it. We don't have to think about it. Let's use it. So that's what we have. So this is something that you want to be sure that you remember. So I can guarantee this is going to show up in your test. So when you're doing the binary search, it's going to return minus k minus 1. So that means that if I didn't find it, what you're looking for, I am going to give you a position that you can insert it. So in this case, I was looking for 7. It's going to return me number minus 3. That means if I apply minus k minus 1, the position 2 would be the one that I can insert this. So if you search using the binary search, it's going to give you the position that you can insert that if you want to insert. Does that make sense? I want you to be sure that you understand this. I can guarantee you this is going to show up on your test.
Yes, it makes sense.
Yeah, okay, thank you. Okay, now, this is very, very important. So when we are comparing objects, so when I have arrays of objects, when I call the sort, the sorts need, any kind of a sort that I do, it needs to know which one is smaller than the other one, which one is bigger than the other one, or which ones are equal. So that means I have to have my compare to method implemented. In the last test, some of you guys didn't know about compare to. So if I don't have compare to implemented, and I'm going to call the sort method, it's going to be, remember, the default compare to is going to do what? It's going to be comparing the addresses of the object, not the value. So if I am going to be sorting my object, I have to be sure that I have my compare to implemented. So if I'm comparing students, what is it that I'm comparing? Am I comparing their age? Am I comparing their grade? So I have to have that compare to, which is going to be called by my sort mechanism. So the compare to is going to return 0 if they are equal. It's going to give me a positive number if the second one is bigger. It's going to give me a negative number if it's smaller. So who's going to define that? The class or the objects that I'm going to be using is going to have that compare to. It has to be implemented in it. Otherwise, this sorting is not going to work. So if I have country, when I'm comparing two objects of country, what is it that I'm comparing to? Am I comparing the area? Am I comparing their income? Am I comparing the amount of income through import? Oh, I'm sorry, export? Am I comparing their import amount? What is it that I am comparing? Am I comparing the difference between import and export? So that's something that the object that I'm going to be using that's coming from one of you has to have that compare to in it. Remember, we are all not going to do the same thing. We are going to be doing different things. So when you are creating your object for country, I'm not going to be looking at your code somewhere, somehow, you have to tell me if you have that compared to in there or not. Otherwise, I cannot sort it. Okay, this lambda expression, we didn't spend enough time on it. I think it's a very, very powerful tool. I don't recall saying it, any of you guys doing it. So we can do multiple things at the same time. And basically, when you're looking at the lambda, that means we're creating a function without creating a function. So they call it anonymous functions. Maybe you guys went over it through function pointer or something like that in your C++. I know the previous instructor, Dr. Wilkerson, was going over it. I'm not sure if any of current instructors go over it or not. So what we are doing, we are using this arrow in there. So we are passing two arrays, and then we say we're comparing the lengths of the first one, the lengths of the second one, and then we're going to return it. So that's basically what it's going to do. So this is going to be sorting a string by increasing lengths. I would strongly suggest you guys go over this lambda expression, try to use it a couple of times. It's a very powerful thing, but we didn't basically cover it in our class. And hey, you're learning new things, put it in your final project. Don't worry about it. So I think that's all I have for you guys for today. Questions, concerns?
I have a couple questions on the final